So in 4.6, we're going to go on to limits at infinity. These are special cases. We've covered related rates so far in this unit, and so this is just a topic that won't take up a whole lot of time or our energy. So this unit is just going to have a few other topics that we cover besides the related rates. You'll notice we're skipping 4.5, and we won't be covering that. We don't need to. We won't worry about it. But I'm going to start by reminding you about limits at infinity. So when you were introduced to limits at infinity last year, we talked about when n is any power of x that is a positive integer, and c is just a constant. We found that as we divide a number by a bigger and bigger and bigger power of x, as x gets really, really large, this number actually gets smaller and closer to 0. So we start with this. And that led us to our 3 special cases. So first, our function could be something like x plus 3 over x squared plus 1. And this limit at infinity would be 0, and we called it bottom heavy. Or second, we could have a limit like x squared plus 3 over x plus 1, which was top heavy, and top heavy limits do not exist. For our third special case, 3 minus x squared over 2x squared, we have the same highest power as the top and the bottom. So our answer here was just the leading coefficients. Negative 1 over 2 would be negative 1/2. So more x's on the bottom, more x's on the top, or the same amount of x's on the bottom and the top. So applying that to our new special cases today, okay, we're going to do the same thing and evaluate the limits. Before, it really didn't matter if this at x approaches infinity or negative infinity, but in some of these special cases, it will matter. Okay? So in our first example, let's say we have the function 3x minus 2 over the square root of 2x squared plus 1, and we would like to know the limit here. The limit of f as x approaches infinity. So let's call this part A. All right, so a little tricky here because of the square root. So we have to think about this. If I were to take the square root of x squared, what would it give us? Well, it would give us a single x. And then what about its leading term? So the leading term here, the square root of 2, would just be the square root of 2. So now in comparing the top to the bottom, I have the same highest power of x. I have x to the first on top and x to the first on the bottom. So my answer here should just be the ratio of the leading coefficients, which is 3 over root 2. That's what we're going to get. We don't have to rationalize that, so we are going to leave that as our answer. So how is this different? Let's see part B. The limit of our function as x approaches negative infinity. This is going to change our answer just a little bit. Because we're approaching negative infinity this time, we have to multiply our answer by a negative. So where my answer before is just 3 over root 2, I now have negative 3 over root 2. And that's it. That's how it differs. And we're just going to practice this a few more times. So here t is 7 minus 5x over the square root of 4 plus 36x squared. So looking at comparing the top to the bottom, the top is 5x to the first. On the bottom, this term, if I took the square root of x squared, would be x. And the square root of its leading 36, square root of 36 would be 6. So again, I have the same highest power as the top as the bottom. So part A, my limit of g as x approaches infinity would just be the ratio of the leading coefficients, negative 5 over 6. All right, that's part A. But in part B, if I say find the limit of g as x approaches negative infinity, I now have to multiply my answer by a negative number. So if I multiply negative 5, 6 by a negative, so the opposite of negative 5 over 6 is going to come out to 5 over 6. So what you'll end up with here is one time the answer is positive, one time the answer is negative. Negative, positive. And it just depends on what the original answer was. Was it already positive and now becomes negative? Was it already negative and now becomes positive? These two special cases happen because of the square root functions that we're starting with here. So we're going to watch out for those square roots. Right. So we have just one more example, and this one's also a special case, but it's not going to have a square root function in it. Instead, the limit as x approaches infinity of sine x over x. These are going to have trig values. Sine, maybe cosine, maybe you'll even see tangent, but probably not. It's mostly sine and cosine that you'll run into. Now, this may look like our special trig limit, but it is not, and that's because we're approaching infinity, not 0. So this is not my special trig limit. Okay? So its value is not necessarily going to be 1, and I'll tell you it is not 1. So all we have to do is think here, what happens as x gets really, really large? So on top, as sine of a number gets really, really big, well, think of a sine graph. A sine graph as x gets really, really big, just keeps going. And the best I could do is say 1, maybe negative 1. It could be 0 or anything in between. The key here is that the top is a finite value. Similar to saying it's a constant, right? We would get some number out of the top. It could be 1, 0, negative 1, but it stops. It doesn't keep growing. So what about x on the bottom? So if I think about the graph of y equals x, as x gets really, really big out to the right, what happens to my function's value? It also gets really, really large. So if I have a finite value, like a constant, over an infinite value that just keeps getting bigger and bigger, what is a number like 1 divided by a number like 1 million or 1 over 1 billion or so on? What happens here to this value? It just keeps getting smaller and smaller and smaller and approaches 0. So I guess you could think of this as another special trig limit. This one is at infinity, not at 0. Okay. The answer here is 0. And you could do this again if I replace sine with cosine. I would get the same thing. So let's do that. We could even make the bottom something more interesting, like root 2x. It doesn't matter. Cosine just kind of does the same thing here as sine, and it has a finite value on top. On the bottom, this is just a coefficient of root 2. It doesn't really matter. X is just going to keep getting bigger and bigger and bigger. So it's finite over infinite. And if I have a small number on the top and a large number on the bottom, my limit always goes to 0.